Now let's discuss some practicalities about how we apply any kind of finite element analysis to buckling problems. I'll start with the linear buckling problem and then we'll move on to the geometric nonlinearity addition to it. Now, any kind of analysis that is commonly used for columns or for flat plates, the first step that you do for the analysis is to load the structure with an arbitrary reference load. Yeah, you apply a certain reference load and you can call it a certain external load R reference. We perform a standard linear analysis on this and you are able then to get the membrane stresses or the element stresses, or which can also be written as membrane stresses in the plate at this load. For stresses that are associated with this load RF, you will have a geometric stiffness matrix which will be referred to as Kg, also ref. Now for some other load, as long as it is a linear analysis, you can have a multiplication factor lambda. So if you have a certain external load RF and related to that you have a certain geometric stiffness Kg ref, then if I multiply the reference load by lambda, then I will also have the Kg ref multiplied by lambda. So this implies that multiplication of all the loads is also going to multiply the intensity of the stress field. Because this problem is presumed linear, the conventional stiffness matrix remains unchanged. Right? The regular one, which is Km, will remain unchanged. Now let's say that there is a buckling displacement which is applied to it. So for example, the standard according for the RF, you had the displacements to be equal to U ref. Now for, I don't want to call it capital U because we are continuously using it for the energy term. So let's switch to something called displacement, so D ref. Now if we apply a certain small change in displacement for buckling. So if I say for buckling, I apply a small displacement delta D, which takes place relative to the displacement D ref for the reference configuration. Because for buckling, the external load R ref cannot be changed at the bifurcation point exactly where the buckling occurs, we can write the stiffness, which is K, so we can also write it as Km, plus a critical multiplication factor, let's say, at which buckling occurs. You have the geometric stiffness Kg ref times the displacement D ref to be equal to the critical R ref. Now when buckling, when the displacement is applied, then everything else remains unchanged except for D ref has a certain extra displacement delta D attached to it. However, the reference load does not change because the load, external load without the change in it, that's when the equilibrium is lost. So if I subtract the first equation from the second equation, so if I write this as 1 and this as 2, then 2 minus 1 will give me Km plus lambda critical of Kg ref times delta D is equal to 0. Now this is very simply an eigenvalue problem, and we have seen this before when we were trying to solve this problem also using the energy-based method for the column buckling. Now delta D therefore is the eigenvector, but before that you have your load which is applied, so your R, the critical load, which was equal to lambda critical times R ref, is given as the eigenvalue for this problem. And the delta D that is associated with this situation is then called the eigenmode for the analysis, and lambda critical here is called the eigenvalue for the buckling. Now because the magnitude is indeterminate, it's a linear buckling problem, we will only get a shape from the delta D, but not really an amplitude. Yeah, for that you would have to apply the changes with respect to lambda critical. Now, physical interpretation of this problem can also be seen as an opposite way. Now, because you have the total forces, the stiffness times the delta D, they are totally zero, one can say that the stiffness has to reduce to zero with respect to the buckling mode for it to happen, because delta D must happen. There has to be a change in the displacement. So the stiffness has to be lost. It becomes a singularity and therefore gives rise to this bifurcation in the primary path of the problem. I hope this is clear to you. We will discuss further some changes with respect to nonlinear buckling. For example, a buckling problem will become nonlinear when there is a significant pre-buckling rotation that happens. So therefore, what will happen is that the tangent stiffness matrix, which we have been ignoring so far for changing, will also start changing as well as with the effect of the geometric stiffness matrix. So if the Km also starts changing and updating, that's where the nonlinearity comes in. A simple buckling problem will become a nonlinear problem when, apart from the changes that happen on the Kg, which is the geometric stiffness that we have been considering, there are also changes that happen in Km, or simply put, K. So when we are calculating the tangent stiffness matrix for the problem, then for each step with the change in load, the tangent stiffness has to be updated. Now this update may happen depending on the kind of problem it is. So for example, let's consider a sandwich construction. In a sandwich construction, there is a lot of shear deformation of the core that happens. So there has to be a change in the way the load is applied. So that needs to be taken into account. That means the load is actually changing with the displacement that occurs in the problem. Another example is for instance a balloon problem, where you have a membrane which is loaded with hydrostatic pressure from internally, and the shells are which you can consider as smaller elements have to expand by a very large amount because they are capable of stretching. They are membranes, and at the same time they undergo really large displacements with respect to their reference situation, and in that case as well the KT needs to be updated. In the balloon problem itself with the membranes, the loads are also going to be updated as a result of the change in the displacement. So if you have a buckling problem in which the loads are going to also be updated, or there's going to be changes within the material, etc., then you have to follow the non-linear buckling problem. We have already used some solvers that make use of these situations, such as the Newton-Raphson methods, which are very suited for local buckling problems, and arc length methods, which are suited for global buckling problems. Some things that you need to take care of is that you of course have the load increment, which is meant by the increment scheme that you apply in your nonlinear analysis. When the limit point is approached in a buckling analysis, the KT, or the tangent stiffness, will become singular.